Okay, so I'm Arnab. I'm from IIT Delhi Center for Biomedical Engineering, and I'm also jointly affiliated with AIMS. So today my presentation will be on artificial tissues for surgical training specifically, and what kind of opportunities, research and business wise we have in India. Okay, so first of all I would like to start with the introduction on soft tissues. What is a soft tissue exactly? So soft tissue can be treated very similar to a composite material, which is made up of two constituents, which is fibers, hard fibers within a softer matrix, and this forms a two-layer shape, like which we can stack together to form a composite material, and this has very specific properties which we can tune it to. Soft tissue is very similar to a composite material, like it has soft fibers which are collagenous and elastin fibers, which are embedded within a softer matrix such as extracellular matrix, for example the human heart. So here in the figure we are looking at a heart matrix, and within that a very complex organization of heart fibers. Okay, they together form the human heart, and this exhibits a very anisotropic property. I'll get into all those details. Okay, next slide please, Dr. Mega. Thank you. So just a quick introduction on some of these major soft tissues on the human body. The most common is the human skin, which covers a majority of the human body. It is a three layers. It has three layers, namely the epidermis, dermis, and hypodermis. Epidermis being the top layer, dermis being the layer in which the blood vessels kind of come into. So if you cut your fingers, you are looking at the dermis. It's a dermal cut, and then there is a hypodermis, which is basically includes the fat and the kind of the dermal layer together. And this is a highly anisotropic structure, meaning if you cut a piece of skin, like from let's say my face versus somewhere on my arm, it's going to behave completely differently mechanically. So if I'm stretching this will behave very differently. So what we're looking at here in the figure, this human figure here, is basically these are called Langer lines. So Langer lines meaning the fiber lines of the human body. Okay, so if we cut a piece here, which here is shown as form of a dog bone specimen, from somewhere on the back, on the top of the back versus the bottom of the back at a different orientation, it's going to give a completely different property. So that is what an anisotropy means. So the soft tissue behaves very differently from different directions. Second is a brain tissue. There are two types of brain tissue components. One is white matter and gray matter. They're called transversely isotropic, meaning if you pull in one direction, and if you pull in the other direction, the property is going to be different. However, like in between, the properties might be similar. The third one is a much more complex segment, which is a artery, which has three layers. However, like not in a flat manner. They are all wrapped together in cylindrical manner, and there is an intima, media, and adventitial layers. Every layer has different set of fibers organized in a different way. So tissue is not very simple, material. It's a very complex form of material, which has fibers within a matrix. Next slide, please. Okay, so coming to the need for artificial tissues. Why do we need artificial tissues when there are soft tissues? What is the exact need? So we need artificial tissues for realistic surgical training. So up to date, what we have for, I think I'm missing your slide, sorry. Yeah, so I'll come back to it. Just give me 1 second, please. Yeah, I can see your slide again. Thank you. So basically, right now, cadavers are the ones which are used in a hospital, for artificial tissue and surgical training. So every year, lots of doctors, before they operate on you or me, like needs to really train a lot on different kinds of soft tissues. And our entire human body has just bones and soft tissues. Every organ has soft tissues. However, like maintaining a cadaver and actually getting a cadaver is much more difficult, being like than saying, like getting it into a medical school, you have to go through a lot of ethical approvals. There are maintenance issue. You need a right amount of freezers and like right amount of hydration, otherwise the tissue might go bad, and these kind of issues attract a lot of biosafety issues. So something might get contaminated and cause a some kind of human disease, and they have ethical grounds, of course. So that is one of the key need for moving into artificial tissues. So why don't we have artificial tissues so far? Like, do we not have it? We do have a lot of artificial tissues out there. However, like, the realism in terms of mechanical properties and the feel of that artificial tissue is not very similar to the actual cadaver or to an actual human tissue. So that is one of the key reason we need artificial tissues which are much more better. So there is a huge demand, like I said, in medical schools and hospitals and across many other areas, such as we're looking at some pictures here just to give you an insight. One is a prosthetic. So a lot of prosthetic limbs require artificial tissue as close to, let's say, skin or human muscles as possible. If you don't have it, like, the feel or effect which you have on the amputee's body, like, might be very different. Second option is, you have an artificial heart model which you're trying to do some training on, in your hospital. So the issue is, if this is not very realistic in terms of mechanical and properties and feel, this is not going to serve the purpose. So the amount of suturing force which I'm applying here as a, let's say, a doctor, it's not going to be the same when I actually go to a OT and, like, perform an operation. Like, so a lot of things are very dissimilar when we go to the actual training part versus what a doctor actually delivers. So that's why we need artificial tissues. So the material properties, like I said, needs to be similar, the field needs to be similar, it needs to be biosafe, and for India specifically, we need a low cost priced artificial tissues so that this can be highly disseminated into different hospitals. Next slide, please. Thank you. So let's start with artificial skin, which is the most talked about. And almost 40 years of research has gone into artificial skin development. And what has not been achieved so far, unfortunately, is most of these tissue surrogates or artificial mimics, which we call, of the skin, are actually very different in mechanical properties from the real skin. So if you look at the graph on the left, we are looking at the human skin, which is the orange skinnish color, and we are looking at porcine skin, which is basically a pig skin, and some gels in the bottom. So these are stress versus strain plots, mechanical properties plot, basically. And we are trying to compare how they look at. And why are we comparing this porcine skin? Because these are the surrogates or simulants which are used to replace this artificial skin. So in a lab for training, they are providing pig skin or some gels to train surgeons. However, like, in an actual OT, you're looking at an actual soft tissue. So we have come up with some artificial skin compositions which are the most closest to the human skin. So and this is protected from a US patent which I was working on for a while. So synthetic artificial skin, and I'll go a little bit more into the depth of how the mechanical properties look at. Next slide, please. Okay. So what is the main agenda here to make this artificial skin? So the idea is very simple and clean. It's like, we have to match the human skin mechanical properties, okay, with a low cost mass producible material. That's a very simple agenda, but very difficult to obtain, because we don't have knowledge of how the skin properties are actually, and we don't have knowledge of how the mimic material properties has to be. So that's why we have performed extensive research on this area and tested. The first figure on the top, we are looking at some human skin samples which are being tested in the lab for tensile and compression tests. And then we have come out with some mimic compositions using elastomeric materials such as silicons and gels, making different compositions to come as close to possible, like, to the skin. So that's been the idea. So what is the use of this idea? Let's say we have developed the skin which is mechanically similar to the natural skin. uh, so the idea is twofold or threefold. First is, this can be used in wound suture experiments, which will be exactly similar to as if you are performing a wound suture experiment on a human body, which is not possible ethically, but you can do it on an artificial tissue. Second is standardizing suture practices. So, like, to date, every surgeon sutures or performs a surgery in their own way. they have, this is an acquired knowledge, and this differs a lot from one surgeon to surgeon, you know, like in terms of how much suture force, what is the suture distances. So these kind of standardized practices can be made if we have an artificial material to run a lot of tests on. Second is determine suture forces for robotic surgery. So a lot of these surgeries are changing these days to robotic surgery. So robots are not like trained surgeons, you have to feed something to them. So in order to do that, we have to use this artificial material and run a lot of tests and feed the right information to this robot, saying this much is the suture force, pull it this much, and perform the surgery like that. So this is another use. The third one is training of suture practices for different wound sizes, shapes, molds, skin tags, and removal. And here is a product which we came out with from my company in US. It's called BioFit Technologies. This product is basically a uh, we call it biofidelic, which meaning like it mimics the skin to the most extent so far. Suture pad, so which has lots of different kinds of common wound shapes, molds, skin tags, which you can operate on as a surgeon or a trainee, and practice very similarly as if you're doing on the real skin. Okay. Second slide, please. Next slide. Okay, so coming into a little bit on the technical ground, but I'll try to keep it very brief, like assuming participants are from all the backgrounds. So what we are looking at this very complex graph with a lot of lines is basically two things. We have run a lot of different compositions. So we have made, let's say, 40% of this, 20% of this kind of silicon, we have made a composition. So we have made hundreds of compositions to see what the mechanical properties, which is measured in terms of stress versus strain, looks like. So all this kind of dotted lines and like which are not hard lines are all those compositions which have been tested. And we see two hard lines, which is called skin upper bound and skin lower bound. So these are specifically to natural skin. So if we take an actual skin sample from a human body or a cadaver and test them, this is the maximum extent in which the stress strain profile can go into. So these are the end caps, upper bound and lower bound. So if any of our material composition falls within this upper and lower bound, we can call them some form of skin. Okay, so that's the idea here. So we keep on reiterating on different compositions and compare, does it fall within this range? If it does fall within this range, we know it's some form of skin. Why am I saying some form of skin? Because like I've said, skin property varies a lot from head to toe. So this boundary with the skin upper bound and lower bound takes into account all the skin properties together. So if I get any specific line here, I can say this is probably skin from the head or like palm or somewhere, you know. So we have to run further tests to make sure this is feasible. We run repeatability tests, reproducibility test, ultimate tensile stress, does it fracture similar to the actual skin? These kind of tests are run on the backside to make sure this material is completely, we can call it artificial skin. So next one, please. Next slide. Okay, so there is another type of artificial skin. The shortcoming with the previous synthetic artificial skin, which I was talking about, is it is a synthetic material. It is a polymeric material which doesn't have any hydration feeling. So most of the, so for example, we all sweat, you know, like skin is optimally hydrated at all times. If your skin really dries up, you get wrinkles and there are other things which shows up. So basically, the skin hydration is a very important parameter, not while suturing probably, but while you're looking at a plastic surgery component or some other kind of surgery, which is a much more advanced skin surgery. So there is an advanced version of artificial skin, which is called hydrogel based synthetic skin. Much more difficult to develop, includes a lot of chemistry. So here we are basically looking at some of the chemistries in the cost breakup and also in the graph. But the end goal is we are looking at the human skin properties, and the green line, which we see here, is the skin material property which we have achieved using this chemistry. You know, like that's very close to skin. But this needs a lot of complex knowledge. It's not that easy as the other one. So if we look at the cost breakup, this is a very essential component, because if it is expensive, we cannot sell it in India. You know, like, so this comes down to around 500 rupees per kilogram equivalent of silicon. What does that mean? So silicon is kind of a gold standard for all kinds of soft tissues used in the market. But this specific hydrogel based, we have compared the price and looked at that if we are looking at per kg, it's a 500 rupees. Next slide, please. Okay. So something more exciting than skin, like what other soft tissues we have. So the second one comes out to be an artificial artery. So we all know, like about the amount of heart attacks or heart problems Indians are facing right now in this 21st generation. It's in the Western world as well, but heart problems are escalating like anything else. So there are a lot of stent placement. Stent is basically a device which is placed within an artery when it gets blocked. So due to a lot of junk food which we are eating these days and like unhealthy lifestyle, the arteries get clogged, and basically then blood cannot flow through that, and you might get a heart attack if the condition is very poor. So basically a doctor places a stent to open that kind of an artery. So in order to really simulate a stent replacement surgery or stent placement surgery, we need artificial arteries, and also to understand an arterial condition. Okay, so the way we do this is basically we take an MRI image, a bunch of MRI image, not a single image, of an arterial platform. Like let's say there is a certain patient and we take pictures of his artery at different lengths, okay, length scales, and then we form a 3D model using that, which kind of gives that arterial section which is vulnerable, where we are trying to focus our attention. Then we 3D print that and use our innovative materials to make 3 layers of these arteries grow on that. So this technology is proprietary, protected by patent. This arterial 3 layers, exactly the same layer thicknesses and the same layer based properties, which are shown on the small graph in the top. Like we are looking at the same properties which I was talking about in the skin as well. So we have simulated the properties for the material, and then we have used MRI and 3D scanning along with it to generate these arterial models. So these kind of arterial models can be generated for any person, and we can specifically look at what is the blockage, what is the condition, how to place a stent. So these kind of things are not available so far without a picture. So all the doctor does is do an imaging and make a decision based on that, but the 3D model is still not there. Okay, so the next slide please. Thank you. So jumping on to another interesting area, which is artificial brain tissue. So why do we need an artificial brain tissue? One is for brain surgeons if they're trying to look at any kind of specific complex brain surgery. Second is there is an area which is called traumatic brain injury. It's a very common and vulnerable area around the world, meaning if you are driving a vehicle and basically you end up in an accident of some sort, your head hits the, let's say, windshield or steering or somewhere in your car, you get a traumatic brain injury which you do not understand right away, but like later on your brain function deteriorates and like things get really complex. And these kind of accidents might happen when you fall down from a flat of stairs, or you're in a some kind of contact sports game like a volleyball or something else. These kind of injuries happen. So that is an area where artificial brain tissues are widely sought, but they didn't have any artificial brain tissues. So we developed an artificial brain tissue based on our technology, both for gray and white matter, so that they can test on that how much compression or how much force can cause what kind of damage. Okay, next slide please. Okay, so here again some technical details. So we are looking at the 70 20 70 60, and these kind of these are all compositions. So we are looking at our elastomeric compositions, and then looking at the actual gray matter and white matter properties which we have tested using compression. Okay, and this is also done at two different strain rates, 2.5 millimeters per second and 30 millimeters per second, meaning these are two different impact rates. So let's say I stop my car while driving at 20 kilometers per hour. That is a smaller impact than if I was driving at 80 kilometers per hour. So that impact is very heavy. So we want to test this brain tissue sample at these two different impacts. So that's what we're looking at. Okay, next slide please. This is another type of artificial tissue. The previous slide maybe. uh, yeah, thank you. So this is another type of artificial tissue which is called a calcaneal fat tissue. So what does this one mean? There is a calcaneal fat pad which is underneath our human heel. Okay, so bottom of our foot, the heel rests on something called a calcaneal fat pad, and that is a load bearing component for your entire body. So if you walk a lot and if you stand a lot at your job or somewhere else, you are probably going to have some kind of foot pain in form of plantar fasciitis, or if you have diabetes, then there is a different soft tissue problem like which occurs due to that. So one thing which is very common with this calcaneal fat pad gets damaged over time due to lot of impact injuries. Let's say you play football or do some kind of running exercise on a day-to-day basis, this fat pad can get really damaged. So in order to understand what is the amount of damage we have, I cannot risk a person's life. I cannot say let me put a sensor on your heel and let you run for 5 kilometers, let's see how much damage you have caused. That's not ethical, you know. So we have come out with the artificial calcaneal fat pad material, which exactly mimics how your fat pad would be. And basically this one what it helps out at, you can test this at different strain rates, at different impacts. This can be at a very high impact while you're running at a very high speed, or while you're walking this can be a very small impact. So we can look at all kind of impact scenarios using that. And you know how this is useful as doctors can help footwear manufacturers to develop certain kind of footwear with a certain amount of cushioning or insoles based on this kind of data. So this has a lot of clinical implication. Next slide please. Okay, so there is another component to it. If your fat pad is diseased, we have tested at some of the diseased conditions as well. And just because your foot keeps on going through a cyclical loading unloading cycle while we are walking and standing, it's just not one single load. We have to look at the cyclic property, or cyclical, like whichever way we want to say it. So again and again, if we keep on testing, what really happens to that fat pad. So this is how something we can test using this artificial tissue mimic only. Next slide please. Okay, so this is another complex artificial tissue, which is called an artificially anisotropic tissue. So far we were talking about isotropic tissue, meaning like if I pull this tissue from any direction, it's going to behave similarly mechanically. But now we're going towards a much more realistic anisotropic tissue, which has fibers embedded within the soft tissue. So we have a certain mechanical property for the fibers, we have a certain mechanical property for the matrix, and we combine them together, form a composite material. Next slide please. Yeah, thank you. So these are some optimal, you know, like a lot of research really goes on. So I don't wake up in the morning saying like I'm going to make a surrogate for this specific part of the body. That doesn't happen like that. A lot of research and lots of tests go into it. So here we are looking at some of the optimization parameters, like what happens if we increase the number of fibers within the soft tissue, what happens if we increase the fiber spacing, the fiber angle. So these kind of things actually differ inside the human body. So what are the optimization parameters, how the amount of fiber increases the material property or makes it much more stiff versus small amount of fibers changes it. Next slide please. Okay, so this is another interesting artificial tissue which we have developed, which very different from traditional tissues. These are called conductive tissues. So these will exactly mimic the properties of the human tissue as well as be conductive. So why do we need the tissue to be conductive? So these days, like we are moving towards a world of wearable devices, where we want to be able to understand how the tissue is firing, what kind of tissue fatigue is happening, lot of tissue hydration, any kind of tissue damage or any extra pooling. So lots of different phenomena which we are trying to understand using wearable devices. So in order to do that, we'll have to hardware a sensor or hardware a lot of devices along with your body, which looks very bulky, and a normal person, it's very hard to sell that kind of a device unless it's a watch based, which basically captures very little, you know. So we have made the soft tissue conductive now. Now you can place any sensor anywhere without any extra wires, and the current will transfer from the tissue and another end you can have another sensor or some kind of receptor to measure it and throw it into your app. So this is another innovation which we have created, and this is done using a proprietary fabrication technique which includes short carbon fibers, very optimized length and volume fraction. By volume fraction meaning how many fibers within a certain area, that kind of things are optimized, and we make this certain tissue property. Next slide please. So this is another very technical, I'll skip through more of the very research technical things, but just quickly touch upon like what we are trying to look at here, because these are important parameters. So here we are trying to look at the elongation. So let's say I have a limb prosthetics, lower limb prosthetics, which goes through a lot of pulling and tensioning, like because I am like bending my, let's say, foot and like walking on a day-to-day basis. So this is, I have some kind of artificial soft tissue, like which is placed on your foot as the artificial limb. This is constantly being pulled, and I still want to sense something and take some measurements on my app. So I need to be able to make my artificial tissue in such a way that it can go through 1% of elongation, 100% of elongation, and 200% of elongation. You cannot go beyond that while walking. So does the tissue design or artificial tissue design which is conductive remains the same for that? That is not the answer, like it keeps on changing. So when we go from 1% to a 200% elongation, we'll have to optimize the fibers, conductive fibers within this in a very different way. So that's what we're looking at. These are microscopic images. We're looking at some fiber curlings, permanent fiber deformation or curling, which is occurring due to 200% elongation. And this is a concern which we have raised. And based on that, we're addressing the concern by optimizing the material. Next slide, please. Okay, so now kind of summary on the conductive soft tissues, artificial conductive tissues. If you look here, you will look at a bunch of this colored lines. So all the colored lines are real tissue properties from the human body which are being tested, and all the black dotted lines and legendary lines which you're looking at are the artificial tissue compositions. So what we have done here is we have made a lot of compositions and trying to match which ones match with which kind of tissue in the human body, and then we can say, okay, this composition goes for the human artery, this composition goes for a skin from, let's say, your face, and these kind of things. So that way we can very bulk in a bulk or blanket way produce a lot of different tissue surrogates in a single go. Next slide please. Yeah, so we will be talking very briefly on mechanical characterization for computational modeling. So this is a subject which is very mathematical. The only reason I'm introducing this to you is to show the depth of uh, mathematical or theoretical research which goes into formulation of an artificial tissue surrogate, like, or a artificial tissue. How do we actually compare the material property? One is nice to look at the, thank you. So one is nice, we can look at graphs by itself, just to visually compare, but how do we mathematically compare that this is the regression coefficient or this is matching perfectly? So this is the first isotropic hyperelastic model. So hyperelastic is basically a material model, all theoretical, which we use to describe any kind of stress strain property which a material has when we cause it to go through a tension or a compression. Okay, so this model, I'll just give the very basics. If we look at the last equation, we are looking at a sigma, which is the stress, and lambda is basically the strain. It is a function of the strain, it's called stretch, which is basically strain plus 1. So in this isotropic model, what we have is there are no fibers, the entire material is considered to be isotropic or similar in all ends. Similar. So when we apply, so what we can do with this model, next slide please. This is another model where we have the fibers. Okay, so we have described the fibers and the matrix together, but this model has a lot of problems. Transversely isotropic model, these are research terms, transversely meaning it's a vertically, so one direction the property is something, the 90-degree the property is something different, like I've said for the brain tissue, you know. So these equations go into that, but it all boils down to a stress strain equation where you have bunch of parameters, this C1, C2, C3, the bottom equation. So all you have to do is take a sample of the tissue or take a sample of our artificial tissue, take it to a tensile testing machine, test it, find out the stress strain profile and fit it to this equation and find out the value of C1, C2, C3. So that's how you can match the C1, C2, C3 for the artificial and the real tissue and say exactly that this is a perfect match or this is not a perfect match. The problem with this model specifically, it doesn't study the interaction between the fibers and the matrix. Next slide, please. So this is a integrated model which we have come out with. This is called novel anisotropic soft composite model, where we have included all the problems which were faced by all the other models which are there in the literature. Here there is the fiber matrix interaction, meaning when you pull a certain specimen, let's assume the figure on the left is basically a tissue specimen. When we pull this in a certain direction, the fibers also rotate by a certain direction, you know, like the fibers are not really stretching because they have different material properties. So a lot of things happen inside. So can we skip 2-3 slides and go to the yeah, you can, one more slide please, one more skip. Yeah, let's look at this one. So here I don't know why the fibers are not visible, but here we are basically looking at a soft tissue which has multiple layers, and every layer has a different fiber orientation. Okay, so I think it's the version of the windows maybe, but I'll give you the concept. Basically we are looking at an entire soft tissue which has multiple layers with different fiber directions, and based on that we have come up with this big equation, scary looking equation on the right. But this, all this boils down to is it takes into account the orientation of the fibers, the orientation in different layers, how much fibers are present in which layer, and throws out a stress strain equation which is fully functional. We can use that to compare the real and artificial tissues. Okay, next slide please. So let's look at some of the surgical applications which we have about these artificial tissues we have developed so far and the potential which we can look at. Next slide please. Okay, so first issue is a soft tissue damage and repair. So let's assume you have got a cut on your hand due to some kind of injury. You had an accident today, and you go to a doctor, and he or she tells you that you need a stitch. So they suture your wound so that it can heal. But how do you know that this suture is perfect? There might be a trainee suturing it versus a very experienced doctor suturing it. How do you know this is a perfect suturing, this is going to heal your wound within the next 5 days? Let's say you have to go somewhere and be with that wound. So in order to understand that, we have to run a research. So this artificial tissues can be used to train a doctor in different kinds of wound geometry. So here we have come out with some microscopic images of different kinds of wounds which can occur on the human body due to accidents, and we have sutured them. We have sutured them in various different fashions and tried to look at how much is the suture force, what is happening at a global scale. Like when we, assuming this is a skin from your body which is being sutured, what are exactly the parameters or results which are being thrown out? These kind of information a doctor or an engineer cannot give you without an artificial tissue or without the knowledge of soft tissue mechanics, you know, like that's the place I think there is a lot of place to collaborate. So in the figure here we are looking at a soft tissue phantom or a artificial soft tissue, and then we have created a wound. We are looking at how much it is being stretched. So and the third one, we have sutured it and looked at what is happening in the material property of that after the suture. So next slide please. So some very interesting phenomena here. So what we saw is when we test the normal tissue, it gives us a certain stress strain profile. Okay, when we test the tissue with the wound, it gives us a much more lower profile than that, which is intuitive, like the skin kind of degrades when you have a wound. However, like when we use a suture to suture it, the material property will definitely improve. It will come back to its normal, and sometime it is below normal, sometime it is above normal. So what we have realized is when you actually suture your skin, the material properties can get better than what your original skin is. That doesn't mean we have to go out and suture our skin, but like, you know, these are some information which we get. And the outcome of this is, if we over suture a skin, let's say a doctor places 5 sutures versus somebody placing 1 or 2 sutures, it is going to behave differently. So these are some places we can bring about some research, do some standardization, and use this artificial soft tissues to do all kinds of research like that. Next slide, please. Okay, so here we are looking at a little bit different perspective of this same set of wounds which we are looking at in the earlier slide. So in the earlier slide, we are looking from a surgeon's perspective what really happens when you suture. But here, let's assume somebody needs to perform a surgery and needs to have a certain kind of cut in order to do your surgery. Let's say somebody needs to operate on a person's heart, so he needs to make a certain incision or cut on the human body to reach to that heart or reach to a certain organ to perform that surgery. So what kind of cuts are desirable for quick healing versus what kind of cuts are not desirable for quick healing? This is another very open question in research. You know, like a doctor doesn't know, like unless it's from experience, he has gone through like probably hundreds and thousands of uh, surgical experiences, then it's a different story. But for a new trainee who is coming to a medical school, these kind of experiences are not known. Like how do they know what really happens here? So we are looking at some very interesting phenomena with using a technology called digital image correlation. We are trying to see which wound behaves in what kind of way when there is a strain. So next slide, please. Yeah, so here we are looking at a very typical wound, which is an elliptical shaped wound. And here we what we have done is we have mapped the entire strain field. And minded, this is during an experiment, this is not really a computational study. So this is during an experiment. We apply these kind of, it has a video camera and then we capture image, there are some post processing guidelines. So basically this is overall called digital image correlation. So we are looking at the strain distribution around this wound while this is being stretched at different lengths, you know, like, and we observe there is a certain amount of curling in the third figure, meaning like this is the point where the strain is very high. Even though we are applying, let's say, a very low strain, the strain around this wound periphery at this certain point is so high that this can open up the wound even better worse. So this is an information for the doctor that don't go for incisions like this where you have this very sharp edges. So in the figure on the right, we are looking at we have placed 4 points to very dynamically track what are the strains with the different times as we pull this. So this is the extent of research we can go up till in order to understand what really happens in surgical training. Next slide, please. So this is another area which I wanted to just give an example, and there are n number of examples how this soft tissues, surrogates or artificial tissues are applicable. This is one example where something called a hernial mesh testing. So what is a hernia? Just to give you a very brief insight. So hernia is something where an organ protrudes out of your muscles or the skin part or the fat part and basically comes out, and it's an extremely painful process, usually occurs in your abdominal area. You would have heard of hernia if you have studied biology or some basic lessons in that. So close to 20 this one we are looking at a million 20 million hernia repair surgeries per year are reported around the globe. So hernia surgery is usually, so what is a hernia surgery? So the first figure here is where the herniation has happened. Herniation means protrusion, so herniation means coming out or prolapsing. So the organ has come out, so you need to put the organ back surgically in order to not let it come out. Okay, otherwise it's extremely painful, it has damaged the tissue around and the organ is a bare organ. So how do we do that? So the doctor usually what he or she does is they put the organ back and put a surgical mesh, which is a polypropylene elastomeric mesh, and basically sutures that top part so that the mesh kind of creates a hammock in order to not allow that organ to come out. Okay, So in order to prevent this pain and infection, this procedure is done. However, the hernial surgery failures are extremely high. Because of the reason, there is no way to actually evaluate these meshes, how they are going to work in a really after post surgical stage. Like, let's say 2 weeks after a surgery, is this mesh going to get damaged, or is this going to be fine? So that is an open question, and a lot of doctors are facing issues. So there has been some research on just the mesh testing, but nobody has been able to see what really happens, because this mesh is being sutured to a tissue. What really happens when it interacts with the tissue? So there is a lack of artificial tissue on this pelvic soft tissues. So basically, we cannot just take a pelvic tissue from a cadaver and suture it. So that has been done in a few labs in the US and Europe, but not in India specifically. And this hernial mesh is very common. And some tests have been done in very smaller animals such as mice, and like even some primates, but their tissue properties or their body physique or physiological conditions are very different from a human condition, so none of the tests are actually validated on a human body. So next slide please. So what we have done is we have come out with a very specific soft tissue, artificial soft tissue for the pelvis. So we know the material properties, we have tested it, so we came out with a artificial soft tissue for that, and we have sutured the mesh along with it and tested it in under tensile loading, and to understand what really happens. So now that we cannot go inside a human body and perform this, but we can do this at a lab, like with the artificial tissues, with no issue of storing it, because this is just a soft elastomer material. You can throw it in a desk, keep it for 100 days, keep it for 5 years, it's not going to change. So we have conducted a lot of tests, and the figure on the right basically shows we have run some computer simulations as well to look at how they compare along with the normal conditions for an experiment. And also we are looking at that, do we have any key takeaways, because when we perform an experiment we cannot put a sensor at every end. Using a computer model, we can look at very specific or scaled down narrow model parameters, like, and we have tested this under different strain rates, meaning at different speeds. So this mesh, think about, is constantly moving while you're walking, so your abdomen, like where this herniation has occurred and there has been a surgery, this keeps on moving, and this might move at a very high speed versus a low speed. So we have tested at different speed what really happens now in a lab itself, without any need of a doctor. We definitely need to validate this with a doctor, but not now. Next slide please. So not going into the details, so this is just to kind of show you what kind of research capabilities which can have with this artificial tissues. So we have run experiments with at different strain rates, and looked at specifically using the computer model also, that what happens inside the individual components such as the mesh, the soft tissue or the artificial soft tissue, and at the suture point. So a lot of surgeons have said that the sutures break when somebody wears this hernial mesh for a while. The sutures might fail, but the bigger problem is the mesh has been failing a lot. So to pinpoint what the problem is, this surgical training or this surgical experiment can be performed in order to do it outside the body. Next slide please. Also some key results on computer model. We are looking at something very interesting which we have found out. So there are lots of different kinds of meshes. Johnson and Johnson is one company which is a major mesh manufacturer, hernial mesh manufacturer. Each mesh is close to $1,000, so you can imagine how much cost is it goes into it, just from an entrepreneurial perspective. And one mesh surgery failure in the United States, you can go up to $1 million of lawsuit against a doctor. So basically these are some of the issues, and these are coming in India also. Like, the lawsuit might not be that relevant, but there are a lot of issues with the uh, health issues, post surgical health issues. So here we have pinpointed that amongst the 100 different designs of meshes which are pumped out in the economy, like which people are surgeons are putting inside a hernial operation, we have pinpointed what is the issue here. So we have looked at the unit cell design. If you look at some of the designs here in the blue, basically some of the sky blue or the lighter blue condition, that is where the stresses or strains are mainly concentrated. So based on that, we have identified that the unit cell design or the repeating design which is inside that mesh is the main culprit. This is what is occurring, causing like a huge amount of mesh failure. So once we know this, using all our experiments and computation, we can now suggest to a doctor, let's change this mesh design. And think about, you can come out with a patent regarding this, you can come out with your own product line using this. So these are some of the opportunity areas. Next slide, please. So just to kind of conclude what we learned from here, the major issue and why we need artificial tissues is like there are a lot of ethical and biosafety issues associated with cadaveric and live human tests. So live human tests are not ethical. I just cannot go up to a person and perform a surgery and say, this is what I have found out, let's make a product around it. That's not going to happen. And cadavers are very difficult to procure. You need a lot of regulatory approvals and things like that in the hospitals, and a lot of maintenance issues. So that is the main agenda why we need artificial soft tissues, mainly in India, because a lot of these artificial soft tissue variants are already existing in the US and Europe market, very highly priced and not very realistic. India doesn't have a single company which produces artificial tissues. So there is a need for realistic and low cost artificial tissues for surgical training in India. And most research artificial skin, which is the most common artificial tissue which is being made around the world. There are two variants which we have come out with. One is a synthetic variant, very low cost. The second one is a hydrogel based variant, which is a much more sophisticated, when it's for a very sophisticated surgery. We can do that chemistry and make that skin which has the hydration component to it as well. So we have discussed about artificial artery, brain, fat tissues which were being developed, and also artificial anisotropic and conductive tissues which were being discussed, which can have an impact in the prosthetics market. So making characterization needs to be done for comparison with an actual tissue to justify that this artificial tissue is as good as an original tissue. And computational modeling can also be done as an extension to pinpoint some surgical problems or some health issues which we can correct using this variant. And surgical applications which were being discussed includes wound suture research and hernia mesh testing. So this is a fairly big opportunity, and like in India, where we can start surgical soft tissue production at a very low cost. And I'm definitely open to any suggestions and like questions from the audience side. And this is a very new technology which India has a lot of potential, and the market is already existing. It's just not tapped, because right now, the if you try to buy a soft tissue surrogate or an artificial tissue from abroad, it's very expensive. So with that, I would like to conclude my presentation, and thank you all for patiently listening. And I'll just open the board for some questions.
Good afternoon, sir. This is Yogesh. I would really like to
Yes.
appreciate this
Yeah.
extensive
Good afternoon.
work. And my first question is, when we consider artificial skin tissues, especially when speaking about soft tissues, there are organs like brain, which is composed of soft tissues that vary totally within the structure itself. Like if we take hypothalamus, it has a different composition. If we take pons medulla, that has a different composition. If we take a cerebellum or cerebrum, that has a different composition.
Right.
And the hydration also affects because the entire organ is suspended in a cerebrospinal fluid, right? So at that time, what kind of
Sure. Sure.
is it a possible thing to develop an artificial brain tissue?
Right. Yes, sure. So thanks for your question. I think that's a very good question. That brain is such a complex component. Can we put it as a single tissue, or it has to be multiple tissue? So to answer that, brain has there are cerebral arteries as well. There are blood vessels. There is gray matter. There is white matter. There are different components which might have different material properties. So we'll have to pinpoint it to exactly what we are operating in. So for example, in AIMS recently, we had a meeting with a brain surgeon, and he's interested in brain arteries specifically. So we said we can come up with a artificial tissue model for those brain arteries. Just give a few arteries to us, we can test those and we can give you a model. So it's very similar goes to the other components which you have mentioned. If you want to develop a model or a soft artificial tissue surrogate for that, we'll have to specifically look at that component and make one for that. And later on you can it is possible to organize them together to form an entire brain model, you know.
Yes, sir. So the other question is, recently
Sure, please go
in
ahead.
United States there is a startup called Gel that has come up with the next generation band-aid, which is actually a gel when it is injected into a surgical procedure, like an internal organ surgical thing is going on. For example, let us consider a liver surgery. At that time, if we inject the gel, it actually covers the ruptures or areas instead of a suture, and then it after the skin
Mhm,
grows, it is degrading itself. It's biodegradable as well. So what
mhm.
kind of prospects globally would it have over the artificial meshworks or sutures that are coming up?
Yeah, sure. So that is a good question. Actually, the way I would answer this is when you implant something and place it within the body, like you've said for the gel, it has a very different set of regulatory proceedings which goes through. You know, like you need to go for the Food and Drug Administration of the United States, which is FDA. So that goes through a lot of clinical trials and initial proceedings before you can actually inject this gel to a person, you know. So those prospects are very I would say high level, and needs to have a researcher who is working in that field. What we are working on is slightly different. They are not really implantable. So all these soft tissue models which we are working on, these are something which we want to have them as a surgical training model which somebody can prepare or test inside a lab just for suturing or any kind of surgical practice. These do not need any regulatory compliance. These do not need any kind of biosafety things like freezing. So you can just have it and place it somewhere, you know. So that is the
Yes,
way
sir.
to test it. So I think the prospects for this one specifically, surgical training and prosthetics market, the prospect for that is mostly surgeries. So there is a little bit of difference in prospects there, if that
Yes,
answers
sir.
your question.
Yeah. My final question is, in case of,
Sure.
as you said, in case of hernia, when people use meshworks, instead, can they be replaced by synthetic biocompatible nanofibers that can give a drug delivery as well, that can have a drug delivery aspect as well? Because when we are developing artificial skin tissues, it should be similar, it should be possible in a
Mhm,
similar way to create a meshwork also, because both are polymers, both are fibers. Recently, in today's paper, there was an article from
mhm,
IIT Madras that has created a nanofiber for sutures. So
mhm.
that was especially in
Right.
the nanoscale. So how beneficial
Mhm.
would such kind of a regulated drug delivery based nanofiber meshwork similar to artificial skin tissue would be in such cases?
Okay, so yeah, sure. So I think like there has been a lot of changes and like progress in the nanotechnology, but most of them at a clinical level, that is a little bit doubtful. I don't know how most of these technologies are performing clinically, because nanotechnology is a very new field. Like there are a lot of different fiber technologies and things which are coming along, but how this is actually being implemented, that is one question. The second part is what we have come out with is not really for a drug delivery application. So this will definitely have a, like you have said, for the mesh specifically, we will have to test those meshes, you know, like that's where we are looking at. And one of the ideas which we had is, if we can have the, let's say, pelvic mesh for hernia, which can be very similar material property as the pelvic tissue itself. So in that way there is no friction between the tissue, there is no material mismatch or mechanical property mismatch. So those kind of aspects we are looking at. Nano area we have not really looked at. And like I said, from an entrepreneurial standpoint, it might not have too many opportunities. Like that's what my personal belief is. But from a research standpoint, you can definitely go in any direction and like go for more computational research and experimental as well. So that's kind of a just my address from here, you know.
Okay, sir. It was a really
Yeah.
interesting and highly detailed study. Thank
Yeah, thank you for your questions.
Hello, sir. RN this side.
Hi,
Sir,
Arnab.
I have actually a two question. The first one is,
Sure.
sir, how you counter the deformation at the 200% elongation? And the second one is, you mostly in the graphical representation, you have considered the stress strain parameters. So what other factors
Mhm.
that you can consider while designing the artificial tissues?
Sure, sure. Yeah. Okay, so to first of all answer your first question, so for the conductive artificial tissues, like if there is a 200% elongation, let's say, so what really we have to look at the composition here. So there are short carbon fibers which are at an optimized length and kind of distributed in a very optimized manner within a elastomer. So they get all spaced out, like when you keep on stretching this material, they all space out, and the conduction decreases because the amount of cross link kind of decreases. So you need cross links and the wires have to kind of touch each other, like that's the main idea. So in order to have more cross links, we need to increase the amount of fibers and make the fiber distribution much more dense in order to capture that 200% elongation. So if something is applicable for a 200% elongation, that will be a much more stiffer material because it has to capture a lot of fibers. So that is to answer your first question. The second question, how I would answer is, so stress strain profile is a good metric to look at from a mechanical standpoint, how your material or artificial tissue compares with a real tissue. However, like I've said, for the second variant, if hydration is something which the doctor really cares about in a surgery, then you have to provide hydration. So that has to be a hydrogel based system. There are other parameters, like there is a testing called ballistic testing. So in military, like what happens is somebody wants to test a bullet and the effectiveness of that bullet to injure someone, like for example, for a certain gun, let's say. So that kind of a ballistic testing has to be done with some skin based fracture properties. So the skin fracture properties have to be tuned exactly like that. So every artificial tissue has to have a different purpose, like, so this is a very purpose based. So here we are only looking at tensile and compression properties. If we need to look at the fracture properties, we need to specifically focus at variants or compositions which can mimic the fracture properties. If we need hydration, we need to mimic the hydration. If we need a certain structure like the wrinkling or the, let's say, the skin ridge structure on the top, in order to look at skin friction or touching, let's say you're holding a glass, you're doing some kind of robotics project, you're holding a glass, and basically you need to see what amount of friction needs to be put in the arm or skin material in order for that robot to hold the glass. So you need to look at the friction properties by changing the structure. So these are some of the two or three things I can mention, besides like 10 other things which can happen for mimicking skin. So that is where it stands. Did I answer your question?
Yes, sir.
Okay, any other questions, are you?
Hello, sir. Good afternoon.
Yes, sir. This is
Yeah, hi.
I am Satyavati. Actually, sir, my question is how much challenging is it when you do the fast testing in the end users, that artificial tissue? And second question is, sir, how you analyze the adverse reactions of artificial tissue?
Okay, so your first question, can you say that one more time? Like, so you mean end user? Just to kind of reiterate, this is not a transplantable skin. Like I'm not saying that I'm going to give the skin for if you have a wound, you transplant it. This is just specifically for surgical training. So can you tell your first question one more time so that I can answer it properly?
Yes, sir. Maybe that surgical tissue, maybe. But how much challenging is it to bring for the first time to the community? Means to use the first time in the
Okay,
end
okay, I
user.
understand. What you're saying is basically to make it reach the end customer, how difficult it is. It is a very easy process. So all you have to know is basically the composition. So basically what I'll give you is, let's say, material A and material B, which will come in a liquid form, and I'll ask you to mix it, let's say, at a 30 is to 50 ratio or something like that, and you will mix it in that, keep it for 40 minutes, it will be ready, and it will be very similar to skin. Okay, so you can just have this material ready for your dispatch. So if you want to look at skin. If you want to look at any other tissue, I can give you a composition based on our whatever we have done so far, and you just mix it, and that part is ready. If you need hydration, then it is challenging. Like I've said, like if you want to build a hydrogel, then that needs a lot of chemistry, like because chemical and mechanical optimization. So that is a little bit challenging, but for the synthetic variant, it's very easy. It's just a matter of few hours, you can ship your soft tissues anywhere.
Okay, sir. Sir, how you analyze the
Okay.
adverse effects means how it can affect any other tissues or any other part of the body? How you analyze that thing?
No, this has no like, so any kind of adverse effect, this is totally synthetic, it's a dead material. So you cannot analyze the adverse effect, like let's say if this is going to cause any infection or not. That kind of things you cannot analyze. What you can analyze is what really happens if I have a cut or a wound or a suture here, and I want to look at, let's say, how much amount of pressure should be applied during a surgery so that this wound doesn't expand. So these kind of adverse effects you can study, but what really happens to the body, like from an infection or a cellular standpoint or something which triggers your nerves, those kind of things you cannot analyze with your dead material. This is just for training, you know.
Okay, sir. Okay, sir. Thank you, sir.
Yeah, sure. Welcome.
Hello, good afternoon, sir. This is Dixit here.
Yeah, good afternoon. Can you speak a little loudly, please? I cannot hear you.
Yes, sir, Nidhi Dixit here. Sir, my
Hi,
question
Nidhi.
is
Yeah.
that as we know that we have the very delicate organs, sir, what are the basic properties of the artificial tissue which can affect the natural phenomena, and what are the risks while we are using the
I think your
artificial?
voice cracked. I missed out on the part, like, so I could hear till the artificial tissue. Can you say that one more time, please?
Yes, sir. My question is that what are the basic properties of artificial tissue which can
Mhm.
affect the natural phenomena, and what are the risks while we are using the artificial tissue surgery?
Sure, sure. So the major good property is, I'll start with the good properties. So one good thing is this is something which you can carry in your pocket. Basically, you can take it to your home, take it to your lab, and do some suturing practice. Let's say you're a medical student, so there is no biosafety issues. So what are the other good, how do you compare the properties? So basically these properties are all done on the research back end, like, so let's say you want a soft tissue, let's say for the nose, for example, because you want to do some nose surgical training. So you ask me, let's say that Dr. Chanda, give me a the artificial tissue composition. So what I'll do is I'll send you two liquids which are a certain proprietary composition. You will mix those two liquids in a certain ratio, I'll give you, and that will give you the nose material. So then you can, it's a synthetic material, you can take it anywhere and you can perform your surgical training. Okay. So that's the major good thing with this. How this differs from an actual tissue is because two three ways it differs. Like I've said, most of these materials are isotropic, meaning they behave the same way if you pull it or push it from any direction, which is not the same with your skin. So if I pull your let's say if I have a skin specimen or part in my arm, if I pull it in the x direction versus in the y direction, they will behave differently. So that is an isotropic part is different. And the second part is hydration. Most of these skins are actually hydrated, like so you sweat, or usually there is a natural hydration, like which affects the material property. So that kind of hydration, if you want to achieve, you'll have to go for the hydrogel basically.
Yes, sir. So what are the risks while we are using the artificial surgery?
I'm sorry, I could not hear you. Can you be a little loud, please?
Sir, my second question is that what are the risks while we are using the artificial surgery?
You are saying risks, right?
Yes, sir. Yes, sir.
Okay, yeah. What are the risks associated with this? So there is no risk specifically. That is the idea, like, because this is something we are not putting into someone's body or replacing skin or muscles or anything. This is something we are just using in a hospital or in a training institute just for all the medical youngsters who are coming right out of, like, let's say, school, to train on different kinds of. So rather than having trained on a dead body or a cadaver, they are training on this, which is much more safe. They can just, they cannot take a dead body or a cadaver to their home and train it, like. So this is somewhere they can basically sit down anywhere, train on this, and find out how they want to perform a surgery. So there are no really biosafety or ethical risks associated with this.
Okay, sir. Thank you, sir.
Yeah, thank you. Yeah,
Good afternoon, sir.
yeah, good afternoon.
So my name is Pahul, and my question
Can you be
is,
a little loud, please, Parul? Your voice is a little low, please.
hello, am I audible now?
Yes, yes, sure, please go ahead.
Okay. So my question is, sir, can we somehow change the type of skin? As you said that our skin varies from let's suppose heels and arms and other things.
Hmm.
So can we somehow
Yes,
change
absolutely,
the type?
absolutely.
Hmm?
Yes, so
Okay.
we have made composition for all kinds of skin. If you take it from head, arm, toe, anywhere on the body, we have already done that. We know the compositions, and you can make a skin variant for any of the skin from anywhere.
Okay. So my next question says, can we use that fat pad? Okay, the first question with respect to fat pad, that is made up of dead cells.
Hmm.
So can we use that fat
I'm sorry, I
pad?
could not get your second question.
Sir, my first question is
Yeah, please go ahead.
regarding the fat pad, and I'm asking that
Hmm.
these fat pads are made up of dead cells? Question mark.
You said stem cells?
Dead cells. Dead
I'm sorry,
cells.
did you say, no, your voice was not clear. I'm sorry. Could you say that one more time, please?
Okay.
Last thing, what kind of cells did you say?
Dead cells, sir. DEAD, dead cells. That fat pads are
Yeah,
made up
dead
of dead
cells.
cells.
Okay, okay, yeah, sure, sure. So fat pad has both active and passive components. So the structure, it has a microstructural design, and it has an outer structure. So most of these are not dead. Really, you will have a feeling when your fat pad gets really damaged. So they are not really dead. So yeah, so this is not a dead cell. This is a structure which has active components, live cells.
So can we use that fat pad other than using it as a heel of the foot? Can we use it on the patient for suppose on a breast cancer patient type? Can we use that fat pad
Yes,
on
yes.
in that?
Yeah, absolutely, we can. So this is a good question, actually. So what we have done previously is, you know what an insole is, right? Like insole for plantar fasciitis. So basically, any insole, you can attach this extra fat pad surrogate or an artificial fat pad, and that will give support to the already damaged fat pad. Like, so basically you can have that extra insole as a cushion, which doesn't, because what happens with a fat pad degradation or damage is basically the fat pad fat elasticity kind of degrades. So you can support that with an artificial fat pad in an insole, and that will improve your condition.
Okay, sir. Thank you. Thank you.
Yeah, yeah, sure, welcome.
So students, I consider there are no more questions. And if you have any question, you can ask in WhatsApp group or here. And I can share professor's number if he don't mind. Can I share, sir?
Yeah, yeah, absolutely. And students can feel free to email me, or if there are links of, any with other questions or any collaborations, I'm happy to answer those.
Yeah. Thank you so much, sir, for your time and you accepted our invitation for this session. And we always look
Sure.
for your support and guidance for this undergraduate students in such workshop. Thank you so much.
Absolutely. Thank you so much, Dr. Megha, for having me here and for organizing this. And thanks all the students for your time. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.